Begin with H.L. Ahuja's Basic Mathematical Concepts and Optimization Techniques. This is chapter number 5. This will help you immensely, especially if you were not a mathematics background student, or if you want to brush up your mathematics for economics, especially microeconomic mathematics. We will skip on the introduction and start from the second paragraph of introduction just to get an overview. Decision making that involves solving of maximization and minimization problems is called optimization. Therefore, for making efficient decisions, it is necessary for a successful manager to learn the techniques of optimization. It may, however, he noted that popular techniques of optimization are mathematical in nature. In recent years, the use of analytical models of business decision making has increased the importance of the knowledge of techniques of optimization for the students of economics. Mathematical formulation of these analytical models of decision making are expressed in terms of function, which describe economic relationship between various variables. Therefore, to begin with, we will explain the concept of a function and its various important types. Besides, optimization techniques involve the use of differential calculus and its concepts of derivatives. Therefore, after studying the concept of function and its various types, we will proceed to explain the concept of derivative and rules of differentiation. At the end of the chapter, we will give some examples of how differential calculus is used for optimization problems in economics. So this is just a basic overview of what's going to happen in the chapter. Let's dig right in without wasting any time. Functions. A function describes a relationship between two or more than two variables. That is, a function expresses dependence of one variable on one or more than one variable, more other variables. Thus, if the value of a variable y depends on another variable x, we may write y is a function of x. That's how you denote something being a function of something. Basically, functions are a machine. You give them an input or the x variable. Usually it's the x variable. That's how it's generalized, but it could be any other variable as well. Such as, let's say, the price of a particular quantity, commodity, while you're determining the demand of that commodity, which is what we're going to study, the kind of problems, the kind of functions that we're going to study, because we're studying mathematics or mathematical concepts for economics in particular. Well, coming back to what I was saying, functions are basically a machinery where you give them an input or or the independent variable or the exogenous variable, and they give you an output, or the y variable as generalized, or the endogenous variable, which means it is the variable which is determined within the equation, or the dependent variable because it is dependent on the value of the various or one independent variable called the x, or whatever that might be. So that's how you denote a function, which is y is a function of x is denoted as y equals f of x, where f stands for function. This expression 1 is read as y is a function of x. This implies that every value of the variable y is determined by a unique value of variable x. Like I said, in the function 1, y is known as a dependent variable, x is the independent variable. Thus, in function 1, y is called a dependent variable and its value depends on the value of x. Like I just said, further, the independent variable is interpreted as the cause and the dependent variable as the effect. This is again something that you can call, which is cause and effect. So the dependent variable, or the y in this case, can be called an effect, whereas x is called a cause. Why? Because x is causing the value of y to be something. So x is the cause and y is the effect. An important variable which is extensively used in economics is a demand function, which expresses quantity demanded of a commodity as a function of its price. other factors being held constant, again, which is something I just mentioned a while ago. Thus, demand for a commodity X can be described as demand for X. Now, uh, footer or subscript X is basically deciding that this demand D is for X, the variable X, or the commodity X in this case is a function of price of what X. So that's again written in subscript, where dx is a quantity demanded of commodity X and px is its price. Similarly, supply function of a commodity is expressed as Sx equals to f of px, which is the supply of commodity X is a function of its price. Well, it's very intuitive, even very basic economics, that the demand of a particular good or the supply of that particular good is going to be a function of its price, ceteris paribus, which is other factors being held constant. When the value of a variable y depends on more than one variable, let's say x1, x2 to xn, this function is written as in general form as y is a function of all the variables that it depends on. This shows the variable y depends on several independent variables x1, x2 to xn, where n is the number of independent variables. Again, note that in economics we write causes as the independent variables and effect as a dependent variable. Now, this is very predominantly used in economics, although you'll hear it only much later. Uh, but yes, cause and effect is something that economics is going to call um, the independent variables and the dependent variables respectively. For example, demand of a product is generally considered to be a function of its own price of other commodities, which may be substitutes or complements, income of the consumer, taste and preference of the consumer, and advertising expenditure made by a firm to promote its product. So it's going to be a function of all of these things, okay, and that's how it is denoted. The same thing is written down here as well. The exact nature of relation of dependent variable with the independent variables can be known from the specific form of the function. The specific form of a function can take a variety of mathematical forms. Now, it being a function of all of these variables, in this case demand being a function of the price of the commodity, its substitute, the income, taste, advertising, all of this is just an expression to say that demand is a function of all of these things, but the actual value of demand can be calculated only when you have a specific form of that function. What is that function actually or mathematically? We can explain below some specific type of functions, linear and power functions. Let's take right in. A widely used mathematical form for a function is a linear function. A linear function can be stated in this general form. The general equation of a linear function is y is a plus bx, where a and b are positive constants and are called parameters of the function. Note the parameters of functions are variables that are fixed and given in the specific function. The value of constants a and b determine the specific value of a linear function. The linear demand function with price as the only independent variable can be written as this. So quantity demanded equals to a minus b p, where p is the price of that particular commodity. This is how you can give the demand function. Sorry, this is your demand function, a general demand function, a linear demand function. The minus sign before coefficient b indicates the quantity demanded of a commodity is negatively related to the price of a commodity. We of course know this again, but in function terms, this minus sign is basically mathematically what it's saying is that as you increase the value of p, the value of q is going to decrease. Okay, that's why this minus is shown. And economically, of course, you know that quantity demanded and price of a particular commodity are inversely related, which is the more the price of a particular commodity, the less you will demand it. That is, if the price of a commodity falls, its quantity demanded increases, and vice versa. If A equals 7 and B equals zero point 0.5, the linear demand function can be expressed like this. The above specific demand function shows that a unit fall in price of a commodity. If you decrease P by 1 unit, will cause a zero point 0.5 units increase in quantity demanded of that particular commodity. Okay, so if this decreases, this is going to increase. You've already said this, but if this decreases by a value of 1, you know that the quantity demanded is going to increase by 0.5 units. Why? Because P is then going to be 1. Okay. If price P is 0, the second term 0.5p in the demand function drops out and the quantity demanded is equal to 7. Again, very intuitive mathematically. Um, and economically, what you can say about this is that quantity demanded is not dependent on price of a particular commodity at all. Okay. We can take various values of P and find out different quantities, which is QD of a commodity demanded at them, the figure 5.1. We have noted these price quantity combinations on a graph and have obtained a demand curve DD of the commodity representing the given demand function like this. This is very basic economics, and we all would know all of this already, so I'm not going to go too deep into this. It should be noted that contrary to the mathematical practice by convention in economics to represent demand function, we show the independent variable price in the above case of demand function on the y-axis and the dependent variable, the quantity demanded in the present case, on the x-axis. So if you would know, in mathematics, um, you show the independent variable on the x-axis. It is worth noting that the slope of a demand function will represent delta P upon delta Q. Okay. However, if we represent quantity demanded on the y-axis and price on the x-axis, the slope of demand curve would be this. So it's basically showing however you determine or however you show the two functions on x, the function or the two quant the two variables, which is quantity demanded and price, the slope would differ like that. In this case, it says with 1 unit increase in quantity demanded, what is the increase in price? So whatever comes on the y-axis is determined from the x-axis. Okay. Multivariate linear demand function. Linear demand function with more than one independent variables can be written in the following way. So if you have multiple independent variables, you know that independent variables are going to be all of these variables. These are the same variable that we studied right here, this, where b1, b2, b3, b4 are the coefficients of the respective variables. In economics, the effect of variables other than the own price of commodity in the demand function are depicted by shifts in the demand curve. So if any of the other variables, all of these are changing, then the demand curve actually needs to shift. Okay. So for example, if any of these are causing a shift in the demand curve, it could be a rightward demand curve shift, or it could be a leftward demand curve shift. That's something that we'll see later. But yes, so shifting of a demand curve is basically the demand curve going right or left, or upwards and downwards. But okay, so let's see the example. For instance, where income F income M of the consumers increases, consumers will demand more of product X. This implies shifting the demand curve to the right. The linear multivariate function is written in the following form. In this function, the coefficients 0.4, 0.2, 0.2, 0.3, 0.5 show the precise impact of these variables on the dependent variable. Because if you, let's say, increase this by 1, there's going to be an increase of 0.4 in y. Sorry, if you put this 1, or if you increase this by 1, this is going to fall by 0.4. Okay. Power functions. The linear functions stated above are known as first degree functions, where the independent variable x1, x2, x3, etc. are raised to the first power only. You can see that all of them are at first power only. We now turn to explain power functions in economics. Power functions of the quadratic and cubic forms are extensively used. In quadratic function, one or more of the independent variables are squared, that is raised to the second power. Note that power is also referred to as an exponent. Mathematically, it's called an exponent usually. A quadratic function can be written as this. This implies, you already know quadratic functions. This implies that value of the dependent variable y depends on the constant a plus the coefficient b times the value of the independent variable x plus the coefficient c times the square of the variable x. Suppose a is 4, b is 3, c is 2. The quadratic function takes the following specific form. This. We can obtain the different values of y for taking different values of the independent variable x. Quadratic functions are of two types: convex quadratic functions, concave quadratic functions. The form of quadratic functions depends on the size of the coefficient c. Okay, depends on whatever sign this c is going to take, or the coefficient of x square is going to take. Okay. Yeah. Okay. So usually this is called A. This is always called B, and this one is usually called C in mathematics. If you study quadratic functions or a quadratic equation, if at all, that's how you are going to find it. But yes, if A or C in this case, let's just call it C because that's how it's called here, is going to be upward facing parabola. So the coefficient c of x square is positive, that is c is greater than 0. It's called convex quadratic function because the graph is u-shaped. Okay, this one. On the other hand, if coefficient of x square is negative, then we have concave quadratic functions because its graph is inverted u-shaped. Okay, or upward facing parabola and downward facing parabola. It is worth noting that the slope of the curve of convex quadratic functions, as is evident from the u-shape of the case where coefficient of x square is positive, slope is increasing everywhere. On the other hand, in case of concave quadratic functions where coefficient of x square is negative, the slope of its graph is decreasing everywhere. Okay. It should be further noted that in analytical geometry, it is proved that graph of any quadratic function is a parabola which may be either convex or concave. A parabola is a curve. You can underline this if you want. So if you basically draw tangents here, the slope you see is going to be increasing everywhere. But if you draw it here, it's going to be falling. So it keeps falling. It falls everywhere. A parabola is a curve which is turning point, which has a turning point, and unlike the curve of a linear function, its slope is changing at different values of x, like I said. So its value is going to, its slope is going to change at every single value of x. Multivariable quadratic functions, when there are more than one independent variable such as x1 x2, they have a quadratic relationship with a dependent variable y. Such a function is called multivariable quadratic function. In case of two independent variables x1 and x2, such a function may be expressed like this. If such a function is graphically shown, it can be represented by three-dimensional surfaces and not two-dimensional curves. That's why they've not drawn a curve as well. Cubic functions. Cubic function is a power function which there's a third degree to the term, like it's shown here, um, relating to the independent variable. Of course, the independent variable is going to carry this third degree. Thus, a cubic function may have first degree, second degree, and third degree terms. So this is a first degree term, second degree, and this is a third degree term. Sorry. A is the intercept term. This is always the intercept. The one which has x0, x to the 0th power is called the intercept. Okay. If you want, is going to be written everywhere. I think it should be everywhere else as well. Just forgot to highlight it before, but yes, this is going to be the intercept term. The dependent variable x has a first degree, a second degree, and third degree term. When the signs of the coefficients a, b, c, and d are positive, then the value of y will increase by progressively large increments as the value of x increases. Right? So if these are positive, unlike the negative ones that we talked about here in the last page, um, an increase in that particular independent variable causes a decrease in the dependent variable, whereas in this case, because they're positive intercept terms, the dependent variable the independent variable terms have a positive sign, and so they're going to increase the dependent variable as well. However, some have positive signs and the other have negative signs. In the graph of the function, we have both convex and concave segments depending on the values of the coefficient. Such a cubic function where signs of the coefficients of the variable differed can be expressed as this, where the sign of coefficient c is actually negative, in which the sign of coefficient c of variable x square is negative, whereas the coefficient of others are positive. Slopes of functions. In economics, it is important to know the rate at which a variable changes in response. Okay, so in economics, the slope is basically the rate at which a variable is changing in response to a change in another variable. The slope of a variable measures its rate. For example, it is important to know the rate at which quantity demanded of a commodity changes in response to the change in price of a commodity. In the field of economics, we find both linear and non-linear functions. Let us first take the slope of a linear function. Let's say y is a function of x equaling to 2 plus 0.5x. In table 5.1, we have calculated the values of the variable y by taking different values of function x. This is something that we did in linear algebra in school as well. The slope of the function, this between 2 points, say a and b, in figure 5.4 is given by the ratio of change in y to the change in x. Okay, the change in y, this is the y-axis, this is the x-axis. We also determined this while calculating for the demand function, that the change in p to the change in q, similarly the change in y to the change in x is the slope of this particular graph at any given okay, so in between a and b, let's calculate for that. So at point a of the given function, value of variable x is 3. Okay, you see, and corresponding to it, the value of variable y is 3.5. Okay. When the value of x rises from 3 to 4, value of y increases from 3.5 to 4. This is slope of the function this function is given by the change in y. So you see we move from 3.5 to 4, so there's an increase of 0.5 only, whereas if you check for the change in x, you see we move from 3 to 4, so there's a change of 1. So zero point 0.5 is the slope of the function. So since this is a linear graph, the slope is going to remain the same at each and every point, no matter which point you see. This implies that value of y increases by 0.5 when the value of x increases by 1. It should be noted that the slope of a linear function is constant throughout. Like I just said, if it's a linear function, like in this case, it's going to be constant every time. However, the slope of a linear function can be directly known from the linear function itself, and for that purpose there is no need to plot the data. So here we plotted the data, but it's not really required for us to plot any kind of data to determine the slope. You'll see just now what and why I mean, and whatever this function or equation actually contains. However, okay, consider the following linear function. It will be seen from the linear function that when the value of x is 0, the value of y will be equal to a, which is, we've already determined that this is the intercept. Thus a is the y-intercept. So y-intercept, this one, like in this case, if you see the graph of y, the graph or the linear function's graph is actually starting from the point 2. Why? Because y is equal to 2 plus 0.5x. So whenever x is 0, this point is actually 2, 0. Can I say that? Sorry, 0, 2. So x is 0 here and 2 is where the graph starts, and so you don't even need to do this putting x 0 and everything, because of course evidently this is the intercept of y. Further, in this function, b is the coefficient of x and measures the change in y due to the change in x. So when I put x as some value, what is the change that y is facing? Okay, which is the slope that we just said. So b is basically the slope of the function, slope of the linear function. 2 is the y-intercept, that is the value of y when x is 0. 0.5 is the b coefficient, which measures the slope delta y upon delta x of the linear function. Now let's talk about the slope of a non-linear function. We now turn to explain how slope of a non-linear function, say a quadratic function, can be measured. On plotting the non-linear function in a graph, we get a non-linear curve. Non-linear is basically not straight. Let us take the following specific quadratic function. Y is 5 plus 3x plus x square. Okay, we've calculated the various values of y by taking the different values of x, just like we did in the case of a linear function. So you basically just put any arbitrary values of x to find out what the value of y in that particular case will be. The data so obtained have been plotted to the curve in figure 5.5. It will be seen from the figure 5.5 that slope of a line AB, which connects 2 points A and B on a curve representing quadratic function, can be measured by taking the change in the value of y, dividing by the change in the value of x at a point A. Let's see the point A. Value of x is 1. From the graph we can determine that the value of x is de facto 1, or you can put it in the function to determine what the value of y will be, sorry, x will be. We're assuming the value at A is 1, because we ourselves determined that A is actually this point. So at this point A, where the value of x is 1 and the corresponding value of y is 9, and at point B the value of x is 4 and the value of y is 33. So just put it in this equation, in this formula, which is delta y upon delta x, just like we studied here. And the formula of slope is not going to change just because the function changes. Okay. Similarly, the slope of a straight line AC in figure 5.5 can be measured. For AC, let's see. So from A, uh, talking about y first, because it is delta y upon delta x. So calculating for AC, it moves from 9 to 23. Okay, so there's an increase. We don't need to care about the increase and decrease, just saying for now. Just delta y basically just means whatever the change is, it doesn't matter if it's an increase or a decrease. So from moving from A to C, um, 23 minus 9 gives us 14. So numerator is 14. Talking about the denominator, we've moved from 1 to 3, so 2. Okay, so 14 by 2 gives us 7. So 14 by 2 gives us 7. In similar fashion, the slope of AD can be sought. Okay, 6 comes out to be the slope. It will thus be seen that as x delta x decreases, it was 3 between A and B, 2 between A and C, and 1 between A and D. Slope of a nonlinear curve goes on declining, like we just said. If it's a slope, if it's a curve like this, okay, so the slope is keeping on decreasing. It was 8 of the line AB, 7 of AC, and 6 of AD. As x further decreases, slope of the line connecting 2 points of a non-linear curve will further decline. It should also be noticed that the slope of a straight line AD connecting points A and D is very close to the slope of tangent drawn to the curve at point A. As delta x becomes smaller and smaller, slope of the line connecting the 2 points on a curve be will become extremely close to the point of the tangent TT drawn to the curve at point A. Let's see what this intuition is. Therefore, the slope at a point on the non-linear function curve can be measured by the slope of a tangent drawn to the curve at that point. So you see that as you keep on coming closer and closer to the point A, it just is going to become tangential or almost equal to the tangent of that particular point. Okay, so as delta x becomes smaller and smaller, or the change in x, so this change in x becomes smaller and smaller, or the points come closer and closer to A in this particular case, line connecting the 2 points in a curve will become extremely close to the slope of the tangent T drawn to the curve at a point. Okay. So the slope at a point on a linear function curve can be measured by the slope of the tangent drawn to the curve at that point. And tangent का जो slope होगा is it's a line. Tangent is a line. Talking about the optimization techniques, the differential calculus. This is where we begin the optimization techniques now. Optimization technique are an important set of tools required for efficiently managing firms' resources. As the name itself suggests, optimizing. In what follows, we will focus on the use of differential calculus to solve certain types of optimization problems. In a later chapter, we will explain linear programming techniques used for solving constrained optimization problems. Differential calculus, the concept of a derivative. In explaining the slope of a continuous and smooth nonlinear curve, we explained above that when a change in independent variable, that is, change in x, gets smaller and approaches 0, delta y by delta x becomes better approximate of the slope of the function y is equal to fx at a particular point, okay, like a in this case. If delta x is infinitesimally small, delta y by delta x measures the slope of the function at particular point, and it's called the derivative dy by dx of the function with respect to y. Okay? The derivative dy by dx, or more precisely the first derivative of a function, is defined as a limit of the ratio delta y by delta x as delta x approaches 0. Thus, this is what uh, uh, dy by dx is equal to, which is limit change in x approaches 0 delta y by delta x. Because we're saying that it's infinitesimally small. When it is so, that's when delta y by delta x measures the slope of the function or particular point, is called the derivative dy by dx, which is now written in the mathematical form right here. Okay. It is thus evident that derivative of a function shows the change in the value of the dependent variable when the change in the independent variable, which is delta x, becomes infinitesimally small. So, yeah. Okay. Just that particular thing rephrased yet again, same thing said twice. Note that derivative of function y is equal to fx is also written as, so of course you can write it like this as well. Y is equal to f of x, so either you can write dy by dx, or you can write d of fx upon d of x, or this is also one connotation um, which we studied in school as well. As explained above, the derivative of a function at a point measures the slope of the tangent at that point. We've studied this just right here. Ouch. Okay. Sorry about that. Consider figure 5.6, where delta x is equal to x3 minus x1. The slope of the corresponding straight line AB is equal to y3 minus y1 upon x3 minus x1. So let's check x3 and x1. This is x3 and this is x1. The slope of the corresponding straight line AB. Okay. So the slope of AB is going to be the change in y, which is y3 minus y1 written here, and change in the value of x, so x3 minus x1 written here again. When x becomes smaller and is equal to x2 minus x1, which is for AC, slope of that corresponding line AC is equal to similar intuition. It will be seen from figure 5.6 that the slope of line AC is more near to the slope of the tangent TT drawn at point A to the function curve. Okay. Again, we've already seen this in the last graph. Similarly, if delta x is reduced further, slope of the straight line between the two corresponding points will go on becoming closer and closer to the slope of the tangent tt drawn at point A. So as you decrease or as delta x becomes infinitesimally small or approaches or limit delta x approaches 0, all of this is the same thing. Okay. Thus derivative dy by dx is the slope of a function, whether it is linear or non-linear, and represents a change in the dependent variable. So what is it representing? What is it saying? Again, I think this is the third time that the book is repeating this, but should be etched to your brain now because it's said so many times. The dy by dx is basically the slope of any function, um, which is a change brought in the dependent variable, generally y, due to a very small change in the independent variable, generally x. The concept of derivative is extensively used in economics and managerial decision making, especially in solving problems of optimizations such as profit maximization, cost minimization, output and revenue maximization. There are various types of functions, and for them there are different rules of finding derivatives. We will explain below the basic rules of finding derivatives of the various types of functions. Rules of differentiation. The process of finding the derivative of a function is called differentiation. As stated above, derivative of a function represents a change in the dependent variable due to an infinitesimally small change in the independent variable. Dy by dx of a function y is equal to fx. A series of rules have been derived for differentiating various types of functions. We describe below these rules of differentiation. Differentiation is nothing, it's just finding the derivative of function, which is this value. So to find this, what is a process is called differentiation. That's it. So again, both differentiation and derivative of function, differential equation, all of this we've studied already in school. We're repeating all of this for microeconomics and for mathematics for economics because they are imperative to economics. Okay. Derivative of a constant function. Now this is just redefining all of or reinstating all of what we read in school. Could be a revision for a few of us, could be a learning time for for a few of us, but you would recognize, if you had studied this, you would recognize some of these rules. You might need to memorize a few of them, the ones you've forgotten. It's completely all right. So for a constant function, y is equal to fx is equal to a, where a is a constant. The constant a implies that y does not vary on x as x varies, right? So there is no change that x is bringing to y because there is no y. Okay, that is y is independent of x. Okay, I discussed this just a while ago, I think, in some other context, but yes. Therefore, the derivative of a constant function is equal to 0 because there is no change in y which is being triggered due to a change in x, because there is no x. So there is no change in x, and hence there will be no change in y. Thus, in this constant function, dy by dx is going to be 0. So if f of x or y is equal to a, where a is a constant, dy by dx is equal to 0. For example, y is 2.5. This is a graph which is given here. Okay. So no matter what value x is taking, y is equal to 2.5. It will be seen that a constant function is a horizontal line having a 0 slope, which shows that irrespective of the value of variable x, the value of y does not change at all because it is not dependent on x at all. So dy by dx is equal to 0, or a horizontal line. Okay. If you at all want to, you can just mark this. Derivative of a power function. A power function takes the form, let's say, ax to the power b, where a and b are constants. Here a is the coefficient of x term and the variable x is raised to the power b. The derivative of the function is equal to the power b multiplied with the coefficient a times, don't even read all of this. You'd remember something about a to the power x. If I remember correctly, that's how we studied in class 12th or 11th about the derivative of a power function, which is if y is equal to a to the power x, dy by dx is equal to a x to the power a minus 1. Okay. same is the case here. So a is going to remain here. Nothing is going to happen to a because it's a constant function. Sorry, it's a constant or coefficient of the x term. So in itself, it's a constant. What you do is bring down this b, which is the power of the term x, and you decrease the power by 1. This rule for the derivative of power function is this. Let us take some examples of determining the derivative of a power function. If the function 1.5 is the coefficient of the variable x, that is a, and the power b of x is 1, implicit, right? So it's implicit that it's going to be 1. Using the above formula, what you can determine is 1, which is the implicit value or power of x, into 1 plus 5, because it's a constant x to the power x 1 minus 1. The final value is going to be 1 minus 5, because x is raised to the power 0, so it's going to be 1, and 1.5 is the final answer. This is graphically shown in 5.7b. It can be seen from the figure that the slope of the linear function y is equal to 1.5x is a constant is equal to 1.5 over any range of the values of variable x. Also, one thing which is not mentioned here, I'd like to mention, is 1.5 is written, which is implicitly it is a positive value, because of which the slope is upward sloping, because it's positive. 1.5 is positive, hence it's sloping upwards. And at any value any two values, or any value that you take between two of the values of x, or determining the change of x with respect to y, you'll see that all of it boils down to a slope of 1.5 at any range of the values of variable of x. Quadratic power functions, let us take the following example. Y is equal to x square. Its derivative is 2x 2 minus 1. Again, intuition follows from whatever we studied about power functions. To illustrate, we have calculated the values of y associated with the different values of x, so it is going to be symmetric to the y-axis. We plotted the values of x and corresponding values of y to get a u-shaped parabolic curve. It will be seen that derivative dy by dx, or in other words, the slope of the quadratic function, is changing at different values of x. Like we just said, the slope of quadratic functions keep on changing. Some other examples of power function and their derivatives are: for power function y is equal to 3x squared. You bring this 2 down into whatever the coefficient 3 is, and then you decrease the power by 1. Okay. You can follow these examples if at all you need. Let's follow through just stating the fact here, this is going to be a negatively sloped curve, because this is the slope of that particular curve, and when it's negative, it's going to be negative slope. Okay. Derivative of a sum or difference of two functions. The derivative of a sum of the two functions is equal to the sum of the derivative obtained separately of the two functions. Now this is important, especially if you don't remember derivatives. So suppose y is the function of x plus g of x. So f of x and g of x, both of these are functions, by the way. Usually functions are represented as f of x, but g of x is also a function. Where fx and gx are the two unspecified functions of y, is the sum of the two functions. Then the derivative of the sum is, you take the derivative of the first function, add derivative of the second function, again all of them with respect to x of plus. Likewise, the derivative of the difference of the two function, again the same intuition follows. Let's take an example here. So this, you know how to solve this, add both of them, you get this value. Now consider the following profit function, where each of the three terms represent a function. Now these are three terms. Okay, let's just go one by one. So this is going to be d pi by dq, because you're differentiating it with respect to uh, q, okay, which is the level of output, and pi of course is the profit. So the derivative of profit pi with respect to the output q is same. No need to worry, just take out the derivative of this. Now this is a constant, so the derivative of this is going to be 0 without even a second thought. For this 140, then you bring down the power of q, which is implicitly 1, and then you decrease the value of q's implicit power 1 by 1, so it becomes 0. So basically 140 is the only answer you can get. You don't need to do this again and again. When there's a first power or first degree variable given, you basically just write the coefficient of that back here. For this, let's just try to follow what's going to happen. So 10 into bring the power down 2 and then decrease the power by 1. So 20, 10 into 2, 20 q to the power 1, so 20 q, of course negative, okay. Then you just add them up and write whatever is left. Note that the derivative of a constant minus 40 is 0. Derivative of, okay, just writing it back here, derivative of a product of the two functions. Now this is again important. This is more important than adding and subtracting, by the way. The derivative of the product of the two functions is equal to the first function multiplied by the derivative of the second function plus the second function multiplied by the derivative of the first function. Now let's see this one very closely. Dy by dx function x, then you take the derivative of the first, okay, then first or second, let's say second, then you let the second one be and then take the derivative of the first one. Let's talk about this here. So I would suggest you bring that in and then just make it a positive function, and just an addition kind of a function, so you don't need to do this because multiplication is usually a little bit trickier, but let's just solve it from a two function point of view. In this case, derivative of the product of these will be, you keep 5x square as it is, take the derivative of the second function, and you keep the second function as it is, take the derivative of the first one, write it down. Let's see what happens now. So 5x square is as it is, you take the derivative of this function, what's going to happen, 2x. Now again, like I said, the degree is 1 or the power is 1, so you just need to write the coefficient, that's it. And then the constant is anyway 0, so it becomes 2 plus 0, so it becomes 2, okay, plus keeping this right here, you take the function of this, which is you bring this 2 down, 5 into 2, x to the power 2 minus 1 or 1, so it becomes 10x. That's it, as simple as that. Okay, you just take these out and whatever you need to do. Take another example, let's take this one. You keep this as it is, take the derivative of the second one, add the second one as it is, take the derivative of the first one. Now x cube plus x square plus 5 is as it is. If you take the derivative of 2x square, you come down to 4x plus 0 or 4x, plus 2x square plus 3 is as it is. If you take the derivative of x cube plus x square plus 5, you come to 3x square plus 2x, okay, plus 0 of course, and you can just multiply all of this and simplify it to come to this value. Derivative of the quotient of the two functions, if these are the two functions, how do you take the derivative of the both of them? Okay, so the derivative of the quotient of the two functions is equal to the denominator times the derivative of the numerator minus the numerator times the denominator derivative of the denominator, and the whole divided by the denominator squared. Again, it's usually advised that you just calculate this as if it was fx into 1 by gx, okay, because if you compare with this, multiplication is better. Okay, anyways, let's follow through with this intuition. If you want to learn this is a formula or something, you need to revisit this. or mark this or write it down somewhere, but the denominator is kept as it is, and then the uh, derivative of the numerator is taken, then you subtract or minus, the numerator is kept as it is and the denominator is differentiated, and all of that value is then divided by the denominator squared. Okay, let's take this example here. So if fx is this and gx is this, so keep gx as it is, differentiate fx. Now what is the value going to be? 5. Okay, so x minus 1 into 5 minus, keep the numerator as it is, differentiate the denominator, the value is going to come down to 1. So in the numerator we have 5x minus 1 minus 5x plus 2, and the denominator is of course this. Yeah, that's it. Okay, and then of course you can bring this further down, simplify it, come to this. Take another example, keep the denominator as it is, differentiate the numerator, which comes down to a minus 2 right here. Then you keep the numerator as it is and differentiate the denominator 4x, okay, right here, and then you simplify it easily. Let's come to the chain rule. When a variable y is a function of a variable u, which is in turn related to another function x. Okay, if we wish to obtain a derivative of y with respect to x, then we use the chain rule for this purpose. Okay, suppose variable y is a function of the variable u, so y is a function of u, and variable u is a function of variable x, so u is a g of x. Okay, how you can write this is y is equal to function of g of x. Okay, you can write this like this if ever. We might use this, by the way, in economic problems. So this is how you can write. This is what, this is a value of y, by the way. Okay, it's not written here, wonder why. Anyways, okay. So what you can do is, we first find the derivative of the two functions y is equal to fu and u is equal to gx separately, and then multiply them together. For function y is equal to fu, you take dy by du is equal to d of function of u by d of u, and same for u. Okay, then you multiply them together. Why does this intuition follow, by the way? How does this become du by dx? Is because, sorry, I'm so sorry. Okay. Because when you multiply this by this, you basically cancel out the du's. Okay, when you multiply this by this, the du's are going to cancel out, because here it is in the denominator, here is in the, it's in the numerator, so dy by dx is the only thing that remains. Okay, and of course the right hand side. Let's calculate for this. Okay, let us take some examples to illustrate the chain rule. Y is equal to u cube plus 15, and u is 3x squared. Let's try to find out dy by du first. So it's going to be 3u squared, yes, okay, plus 0 of course, so 3u squared, and then you find out what this is going to be, so 6x. Okay, just multiply them, that's it. Substituting u is equal to 3x square in the above, we have this, and that's how the value follows. Because we are differentiating with respect to x. So we keep the value of u back here, to determine what the actual value is going to be, and this is how the value comes out with respect to x of x. This is a summarization, so if you want you can just give this quick read. Differentiation of the functions with two or more than two independent variables, partial derivatives. So far we've been concerned with the differentiation of functions with one independent variable. However, in economics, relations contain two or more than two independent variables about whose uh, use economists and managers of business firms have to take decisions. For example, demand of a product of a firm depends on its price, income of the consumer, price of the substitute, advertising outlay made by the firm to promote the sales of its product, and some others. We have read all of this before. Further, output of a product depends on the amount of labor, capital, raw material, etc. used for the production of a commodity. Other examples of functions from economics and business with two or more independent variables can be given. Where a function has two or more independent variables and each of them has an effect on the value of the dependent variable, we use the concept of partial derivatives. When we have more than one independent variables, we use the partial derivative methodology. It is called partial derivative because in this the effect of only a part of influences on the dependent variable is examined. Okay, so only a part influence is going to be um, examined. A partial derivative of function measures the marginal effect of a change in one variable on the value of the dependent variable, holding constant all other variables. So if y is a function of x1, x2, x3, partial derivative of y with respect to x1 will show the marginal effect of a very small change in x1, keeping x2, x3 constant. That's why it's called partial derivative. Okay, by convention, and to distinguish it from the derivatives of function with one independent variable, for partial derivatives use a lowercase delta. Okay, instead of the lowercase d. So we don't write dy by dx, we write delta y by delta x. However, rules of differentiation and finding partial derivatives are the same in case of derivative of function with a single independent variable, like the ones that we discussed right now. That's the intuition that's going to follow. It is worth noting that in multivariable function, the partial derivative of one independent variable depends on the value at which other independent variables are held constant. That is why the expression of partial derivative of profit function of a firm with two independent variables, products x and y, indicate that d pi, which is the profit with respect to x, depends on the level at which the variable y is held constant. Let's read through this again because it's important. It is worth noting that in multivariable function, when you have multiple variables, the partial derivative of one independent variable, which is what we have discussed right now, keeping the others constant, depends on the value at which the other independent variables are held constant. We will read this through to know what it actually is going to imply. Similarly, the partial derivative of profit function with respect to y indicates that it depends on the value of variable x, which is held constant. So whatever you're holding constant, it depends on the value of that. The economic reasoning for this will become clear if we take a two-factor production function. And this partial derivative of production function with respect to labor implies marginal product of labor. This is a marginal product of labor. One extra unit of labor produces what level of output? Now, as it is well known, marginal product of labor depends only on its own skill and efficiency, but also on how much capital K he has to work with. Now it depends on whatever level of skills you have, but let's say the amount of capital that is given to you is only so much, then your output is also going to depend on that, right? So if I can work with two machines at once but I am given only one, then my product is going to, whatever marginal product I'm giving is going to depend on that particular level of K as well. Generally, the greater amount of capital, the higher will be the marginal productivity of labor. The other thing, all the other things remain same, of course. Your skill, everything, okay. The money you're paid, everything. To illustrate the concept of partial derivative, we take the example of profit function with sales of two products as independent variables. Let's say this is the profit function, where pi is the profits, x and y are the sales of two products being produced by the firm. The function represents the profits of a firm depend on the sales of two products produced by it. Determining the partial derivative of profit, pi function with respect to sales of the product x, treating sales of y as constant from the above function, we obtain. Okay, so so 50x, the coefficient is going to come here. Now taking this, this is going to become 6x, and this is going to become y. Okay, and because y is constant, so both of these terms are going to become 0 and 0. Thus, with partial derivatives, we are able to isolate the marginal effect of profit of the change, marginal effect on profit of the change in the sales of the product x, keeping the sales of y as constant. So we are basically getting whatever effect on profit the sales of the product x is having, while keeping whatever effect on profit the sales of y is having as constant. Note that in finding partial derivatives of the profit function with respect to x, fourth and fifth terms of the profit function are not considered because they do not contain the variable x, so they're basically constants. Likewise, through partial derivatives, we can separate the marginal effect of variation in sales of y on profit while holding x constant. This is what you're going to get. Let's come on to application of differential calculus or derivatives to optimization problems. We have explained above the concept of derivatives and the rules for its differentiation in different type of function because they are widely used in solving problems of optimization in economics. The process of optimization often requires us to determine the maximum or minimum value of a function. Optimization basically is finding out the maximum and minimum of a function. For a function to be maximum or minimum, its first derivatives is 0. Okay, this is more important. Okay, as explained above, derivative of a function measures its slope, which is dx by dy, or delta x by delta y. Therefore, maximization of a function occurs when the derivative is equal to 0. Thus, an important optimization problem facing a business manager is to produce a level of output which maximizes firm's profits. Similarly, optimum use of resources requires that cost be minimized for producing a given level of output. These problems of maximization and minimization can be solved with the use of the concept of derivative. I suggest that you take this function and try to maximize it because it's a profit function. You want to maximize it on your notebooks before looking at the answer here. But for now, let's follow this example. Consider the following profit function where pi is profits, q is the level of output. For the profit pi function to be maximum, its first derivative needs to be 0. Basically, this is the intuition for optimization, maximization, minimization problems. The first derivative has to be 0. Therefore, to find the profit maximizing level of output, we find the derivative of the given set. Let's see what it's going to be. So it's going to be minus 0 or 0 plus 160 minus 20q. That's what it writes here. Setting it equal to 0 because that's what we discussed right now, right? So in order to maximize the profit which is given here, we need to keep the derivative or the slope equal to 0, and this is the slope. So we get q is equal to 8. At 8 units of output, profit will be maximum. This is the intuition, or this is the implication of this particular maximization or optimization problem. Maximization of profits through the use of derivative is graphically shown in figure 5.9. We'll just see it. It will be seen that profit maximization curve reaches its maximum point at point h Therefore, at point h, the slope of the tangent, which measures the value of derivative d pi by dq drawn to the profit curve, is equal to 0. It will be seen that corresponding to maximum profits, point h on the profit function level of output is 8 units. Okay, so the output is 8 when this curve is basically maximized, and this tangent, the slope of this tangent is equal to 0. This is what we're saying basically. Total profit made at 8 units of output can be obtained by substituting, so basically finding out the value of y. Can be obtained by substituting 8 for q in the given profit function. Basically, you will find the level of profit which is plotted in the on the y-axis profits. You get 540 is that this point. Okay, this point is 540. Graphical analysis cannot tell us easily exactly at what point of output profits will be maximum, for it takes time to draw a graph and conclude from it. However, it is easier to use a differential calculus to find the profit maximizing output. For this, we simply put the first derivative of the function, set it equal to 0, and that whatever value you get is the output at which the profit is going to be maximum, and then you put it back in the function of profit function, and to find out the level of profit that you're getting, the maximized level of profit that you're getting at that particular level of output. Second derivative and second order condition for optimization. A problem arises when we use the first derivative of a function to determine its maximum and minimum value. For setting the first derivative of a function equal to 0 and solving the resulting equation for the optimum value of the independent variable does not guarantee that the optimum value will in fact be obtained. Okay. So one problem with this is this methodology of keeping the first derivative equal to 0 does not guarantee the optimum value will in fact be obtained. For the optimum value, the first derivative being equal to 0 is a necessary condition for maximum and minimum, but it's not a sufficient condition. Okay. For example, in a profit function, first derivative is equal to 0 both at maximum and minimum profit levels. To ensure that the derivative is 0 for the profit maximizing level of decision variable, that is output in the present case, profit maximizing level of decision variable, which is output, because that is what is contained in the profit function. According to the second order condition for profit maximization, the second derivative of the profit function must be negative. Thus, if the optimization requires maximization of function, say y is equal to fx, then the second derivative, which is written dy by dx, must be negative. So this is a necessary condition, and this is a sufficient condition. D square y by dx square must be negative. It should be noted that the second derivative of a function is obtained by differentiating the first derivative with respect to the independent variable again. Okay, not again, but yes, you're using the independent variable the second time. In case optimizing requires minimization of the function, as in case of a minimization of cost for producing a given level of output, then the second derivative must be positive. So if you want to solve for the minimization problem, for cost, you need to minimize cost. That's what optimization for cost is. Then you need to bring the second derivative greater than 0. Consider again the case of profit maximization explained above. A profit function curve such as the one drawn in figure 5.10 may have both minimum points and maximum points. It will be seen in figure 5.10 that L, which is point L here, represents the minimum point, and H represents the maximum point of the profit curve. Important thing to note is that both minimum point L and maximum point H, first order condition is going to be, because the slope is going to be 0, right? It's parallel to the x-axis, so the slope, or dx by dq, is going to be 0 in both the cases, which is where the problem is arising. So corresponding to OQ1 plus OQ and OQ2 levels of output. However, at point L, profit is minimum, and at point H, profit is maximum. So in order to find this level H or this level Q2, we need to again differentiate and get a d square y by dx square level less than 0. Okay. Whereas the first derivative measures the slope of the function, the second derivative measures the slope of the first derivative. First derivative measures the slope of the function, second derivative measures the slope of the first derivative. Okay. Thus, in case of profit function, whereas first derivative d pi by dq measures the slope of the profit function curve, that is marginal profit, its second derivative measures the slope of the marginal profit function curve. Since the second derivative of a function when measured at the maximization level is always negative, and when measured at the minimization level is always positive, it can be used to distinguish between the profits, between the points. It's basically giving the intuition behind why it said d square y by dx square should be greater than 0 in order to minimize and less than 0 in order to maximize. For example, if the second derivative in our profit function curve is negative, it implies that profits are maximized at that level where the first derivative is equal to 0. On the other hand, if the second derivative at a point on a profit function where the first derivative is 0 is positive, it shows profits are in fact minimum rather than maximum. It can be easily known from having a look at figure 5.10. It will be seen from its figure that up to point L, marginal profits d pi by dq, that is slope of the total profit curve, is negative and has been causing the total profits to fall. Okay. At point L, d pi by dq becomes 0 and thereafter it becomes positive, and therefore it will cause the total profits to increase. So it's increasing. Then it will hence point L beyond which the second derivative, that is slope of the first derivative, is positive, and since profits will be increasing beyond this point, it cannot be the maximum. Okay. Now consider point H as the total profit corresponding to output level OQ2 at point H. First derivative is again equal to 0, but after the marginal profit d pi by dq becomes negative, as the slope of the total profit curve is negative, as output is expanded beyond Q2. As you increase output, first derivative becomes negative beyond Q2. Yeah, this causes the total profits to fall. This shows that point H is where the first derivative is 0, and also beyond which second derivative, that is slope of the first derivative, becomes negative, is indeed the point of maximum profit. To conclude, we get the following general test for maximum and minimum. If the second derivative of a function is negative at the point where the first derivative is 0, it will represent a point of maximum. If the second derivative of a function is positive at the point where first derivative is 0, it will be the minimum. Coming back to our profit function, you already had 160 minus 220q as the first derivative. For second derivative, just do the same practice. So 160 is a constant, so the derivative of 160 is going to be 0. Minus 20q, only minus 20 is going to be left, and that's what it is. This is now negative, and hence this point at which we are calculating, which is 8 units of output, is de facto the maximum. Okay. We have till Lagrangian to follow through. Constrained optimization. Okay. Minimization problem. This is going to come out very easy now. In some decision making problems, the objective of a manager is to minimize the objective function. For example, efficiency in the use of resources required that a firm should produce at the minimum possible cost per unit of output. For example, the average cost curve or the average cost function Let's say it's given by this particular value. Now a manager is interested to find what level of output, at what level of output the firm will minimize its average cost. This can be obtained by first differentiating AC with respect to Q, okay, uh, and you get 180 plus 1 Q, okay, yeah, minus 180. Setting that equal to 0, you get the level of Q, and now you differentiate it again, okay, uh, for level 180. You see that this is going to be a constant, so it's going to be ignored altogether. The only thing you're left with is 1 and a positive 1, okay, which is greater than 0, and hence the level of Q 180. At this level of output, the AC function is the second derivative of the AC function is positive, and hence it is the minimum average cost of production, or this level of output basically minimizes the AC of production. Uh, Multivariate optimization. As has been explained earlier, when the dependent variable of a function uh, of many independent variables, we use the concept of partial derivatives. So this is the actual one that's going to be used even in your mathematics for economics course. Rules for finding minimization and maximization problems are the same. To minimize or maximize a multivariate function, we set the partial derivative with respect to each independent variable equal to 0 and solve the resulting set of simultaneous equations. Consider this function for profit for two products, which is given by this, where x and y are two independent variables representing levels of output of two products. It is to decide what levels of output of the two products will maximize the profit. Again, we want to maximize this. Differentiating the profit function with respect to x while holding y constant. Okay, so we're keeping y constant. These two terms are eliminated in our mind, and whatever we're left with is 50 minus 4x minus y. That's what we follow through. Same for y. These two terms are just cancelled out in our mind. What we left is minus x minus 8y plus 75. Okay. For maximization of profit, we must set each partial derivative equal to 0. Just the same way that we did in the one variable optimization. So we keep these equal to 0. To solve the above two equations simultaneously, we multiply equation 1 by 8, and we have to add both of these. We just need to simplify it. Whatever way you want to follow, you can follow it to get to a value of 10.45 for x and a value of 8.20 for y. Thus the firm will maximize profits of its produce and sell 10.45 units of x and 8.2 units of y. It should be noted that the second order condition for maximization is also satisfied. Recall that the second order condition, which is based on the value of second order derivative, is used to distinguish between maximization and minimization. However, the second order condition in case of maximization or minimization of a multivariate function is very complex, and therefore we do not attempt to explain that in this text. In all maximization minimization problems involving multivariable function explained in this chapter, we therefore assume that the point at which all partial derivatives are 0, the second order condition for maximization and minimization is satisfied. Those readers who are interested in knowing the second order condition in case of multivariable functions may consult a textbook on differential calculus. Okay, I wanted to read this to you because a lot of you would ask why we did not solve for the second order condition. This is why, because it's very we're assuming, so you will find this in any book that you read, that in case of partial derivatives we don't solve for the second order condition. The last kind of topic that we're left with is constraint optimization. So far we've been concerned with explaining unconstrained optimization, that is maximization or minimization of an objective function when there is no constraint. However, a particular function is given and then a constraint is given. We've not been given a constraint till now. We're just solving for the cost or for the profit function as is. Okay. However, consumers and managers of business firms quite often face decision problems when there are constraints which limit the choice available to them for optimization. For example, a business firm may face a constraint with regard to the limited availability of some crucial raw material, skilled manpower. Constraint may be of the limited productive capacity. As determined by the size of the plant and capital equipment installed. Besides, quite often marketing managers are required to maximize sales subjects to the constraint of a given advertising expenditure at their disposal. So, given a particular advertising expenditure, that is going to be the constraint in this case. Further, financial managers also work under the constraint of a given investment requirement of a firm, and they are required to minimize the cost of raising capital for that purpose. Managers of business firms also face legal and environmental constraints. So, basically, what we're trying to highlight here is that till now we've not solved with constraints in mind, but let us do that now. In all these cases, when individuals face constraint in the decision making to maximize or minimize their objective functions, we have a problem of constraint optimization. It is worth noting that the existence of constraints prevent the achievement of unconstrained optimization. There are two techniques, you can't use the techniques that we used till now. You need to follow both of these methods, either of these methods. Um, they are substitution and Lagrangian multiplier technique. For substitution method, to solve constraint optimization problem is used when constraint equation is simple and not too complex. For example, substitution method to minimize or maximize the objective function is used when it is subject to only one constraint equation of a very simple nature. In this method, we solve the constraint equation for one of the decision variables and substitute that variable in the objective function that is to be maximized or minimized. In this way, this method converts the constraint optimization problem into an unconstrained one. Okay, let's see with the help of an example. Then the same procedure for optimization is applied as we did earlier in this chapter. An example will clarify this. Let us say that the firm is producing two products X and Y, seeks to maximize total profits given by this X and Y, the quantities of the two products. A manager of the firm faces the constraint that the total output of the two products must be equal to 25. This is fairly simple, which is why we can use the substitution method. Otherwise, we always need to go to the Lagrangian method, and it's actually very easy. So you'll see. To solve this constraint optimization, you just basically take out the value of x, put it back here. So substitute this value in the objective function. You get pi is equal to 50 because it's x, so you put this 25 minus x here, minus 2, then again in place of x you put 25 minus y whole squared minus x, which is in place of which 25 minus y comes. So you basically just solve this to get this value, and then you solve this just like any other problem of unconstrained optimization, like we call it here. So to maximize the above profit function, converted into the unconstrained form, we differentiate it with respect to y and set it equal to 0. So for this, what you get is 120 minus 8y equal to 0. You get the value of y. Substituting y, you get the value of x as well. Thus, given the constraint profit will be maximized if the manager of the firm decides to produce 10 units of product x, 15 units of product y. We can find the total profits in this constraint optimum situation by substituting the value of x and y obtained in the given profit function, okay, in order to get the total profit. Let's come to Lagrange. The substitution method for solving constraint optimization problem cannot be used easily when the constraint equation is very complex and therefore cannot be solved for one of the decision variable. Okay. In such case of constraint optimization, we employ the Lagrangian multiplier technique. In this Lagrangian technique of solving constraint optimization problem, a combined equation called Lagrangian function is formed, which incorporates both the original objective function and the constraint equation. This Lagrangian function is formed in a way which ensures that when it is maximized or minimized, the original given objective function is also maximized or minimized. At the same time, it fulfills all the constraint requirements. In creating this Lagrangian function, an artificial variable lambda is used, and it is multiplied by the given constraint function. Having been set equal to 0, lambda is known as a Lagrangian multiplier. Since Lagrangian function incorporates the constraint equation into the objective function, it can be considered as unconstrained optimization. Let us illustrate Lagrangian multiplier technique by taking the constrained optimization problem solved above by substitution method. In that problem, manager of a firm was to maximize the following profit function subject to the constraint where x and y are inputs of the two products produced by the firm. In order to constitute Lagrangian function, we first set the constraint function equal to 0 by bringing all the terms to the left hand side. You're basically going to bring all the terms here to the left, and we get this. The next step in creating Lagrangian function is to multiply the form of the constraint function by unknown artificial factor lambda, and then adding the result to the given objective function. So you add whatever you obtain here into lambda in this, and that's how you get the Lagrangian function. And L pi, because you are trying to maximize pi, so L pi is a Lagrangian function in this case. As stated above, Lagrangian function can be considered as unconstrained optimization function. It will be seen that in this function there are three unknowns, x, y and lambda. Note that the solution that maximizes Lagrangian function will also maximize pi, which is profit. For maximizing Lagrangian, we first find the partial derivatives of Lagrangian with respect to three unknowns x, y and lambda. Okay, this follow from the intuition of differentiation, which we've done multiple times. Now let's try to do that for x, and you can do that for y and lambda similarly. So 50 minus 4x minus y, and there is no, okay, here this one more x, so becomes 50 minus 4x minus y plus lambda, because again there's one more x here. So what do you get from this? Lambda. Okay, same for y and lambda. Note the last equation 3 is the constraint subject to which the original profit function has to be maximized. Last one is the constraint, right? This is the very constraint that came with us. Okay, in fact, Lagrangian function is so constructed that the partial derivative of L pi with respect to lambda always yields the original constraint. Further, since the partial derivative of Lagrange with respect to lambda is set to 0, it not only ensures that the constraint of the optimization problem is fulfilled, but also converts the Lagrangian function into original constrained profit maximization problem, so that the solution to both of them will yield the same result. Now coming to the solving, let us solve the above system of three equations with three unknowns to find the optimal value of x and y. To do that, we can first subtract the equation 2 from 1. Now you can simplify this as in how you want. These are all set equal to 0. So if you come to this, Then multiplying 3 in the third equation, uh, you can find and come to y equals to 15. Substituting the value of y equals to 15 in the constraint function x plus y is equal to 25, we get x. Okay, that's what we wanted to find, x and y. uh, Thus, we find the same optimal values of x and y as we obtained in the substitution method. Lagrange technique of solving constraint optimization is highly significant for two reasons. First, as noted above, when constraint conditions are too many or too complex, it is not feasible to use a substitution method, and therefore, in such cases, it is easier to use a Lagrange technique for solution of constraint optimization problems. In this case, of course, we did solve it from the substitution method, using the substitution method as well, so it was fairly easy. Could be converted to an unconstrained optimization problem and then solved like that very simply. But there are more difficult cases that we come across. We're going to come across budget lines, etc., in which case we might require the Lagrangian method or Lagrangian multiplier method technique. Second, the use of Lagrangian multiplier also provides a decision maker as additional important information. This information is the value of lambda, that is the Lagrangian multiplier itself. The value of lambda has a significant economic interpretation. The value of lambda shows the marginal effect on the solution of the objective function when there is a unit change in the constraint. So if the constraint is changing by a unit, what is the level of change or marginal effect on the solution of the problem, in this case profit. Thus, in our example of profit maximization, the value of lambda indicates a marginal profit caused by 1 unit change in the output of products, that is the change in total profit when output constraint either increases from 25 to 26 or decreases from 25 to 24. What is the level? We'll see what the level is. The value of lambda can be obtained by substituting the solved values of x and y in this particular problem, right? So any of these problems actually. Okay, so we're using the second one here. Thus, in our above example, the value of lambda can be obtained by substituting x equals to 10, y equals to 15 in the second equation. You can use the first one as well, of course, to get plus 5. So, lambda can be interpreted as a marginal profit at the production level of units 25. It shows that if the firm is required to produce 24 units instead of 25, the profit will fall by 5. Okay, it's going to fall by 5 if you decrease the if you want to produce 24 units instead of 25. On the other hand, if the firm were to produce 26 instead of 25 units, the profit will increase by 5 because there's a positive sign here if you see. Okay. Note the Lagrange technique maximizes profits under a constraint, does not solve unconstrained profit maximization. You can't use this for unconstrained profit maximization problems. You can follow for questions here, very good questions that will help you further to understand this even more. If there's any issue, you can refer back to the text in order to get more clarity. Thank you so much for attending this. Have a great day.